Hi, I'm Dan Cole. I'm one of the professors in mechanical engineering at Boston University. I'm also the director of the master's program for mechanical engineering. I guess I've been in this role for about a year and a half now. I work very closely with Anna Maslin, which some of you people may know. She's the administrative director. And we thought it would be good if I did a recording of describing aspects of the master's program. In particular, you all have to, in the end, fill out a planning sheet when you graduate and put the courses in that you've taken and make sure they fall in the right spots. And beyond that, it's really important that you know, well, what are your focus areas? What are the things that you want to go into? And I certainly have found that, even though a lot of people going to the master's program already have a bachelor's in mechanical engineering, they may not be fully aware of all the different possibilities. We have 8 focus areas. So I want to go in and describe that a bit. In addition, LEAP students, probably, they've had a different life before. They may be an English major, history major, or something like that, and they say, I'm interested in going into more technology. I think I have the ability to do it, and for some reason something's clicked in them. They want to move into that area, but they may not be fully aware of, what are all the different technical things that they could go into. So I'm going to try to describe some of that, the pros and cons and things. And you have to remember, I will probably have a bit of a bias. I'm going to try not to. My area is nanotechnology. So I know that area better than the other areas. I think I know a fair bit of a lot of them, but your advisor should be, look to your advisor to get more information in the specific things. But let me try giving an overview here, okay? So the easy part, I'm going to share my screen here. The easy part is just the planning sheet. And so we'll quickly go through that. So, all right, so I'm going to start with this planning sheet. This is for if you're not doing a thesis. And I'm going to try to give some pluses and minuses why you might pick one or the other, doing a thesis or not. Let's just start with this one, actually. This is for mechanical engineering. So you have I'm going to describe 3 different master scenarios, okay? One's mechanical engineering without a thesis. One is mechanical engineering with a thesis. And one is our PD&M, Product Design and Manufacturing master's program. Okay, so 3 things. The first 2 are pretty similar. So in all of them, you have to take 32 credits, which, because we have 4 credit courses, every course is 4 credits, it means 8 courses, okay? So no matter which of these 3 I talk about, 8 courses. So let's look at this one. This is with you're assuming you're not doing a thesis. You would need to pick 3 courses in a focus area. Okay, now I'm going to go over these focus areas. They're attached to this sheet, and we'll get to it in just a second. But there's 8 of them that we have. Examples are like you could get a focus area in acoustics, or my area in nanotechnology, or something like that. Okay, so we'll get to that. You have to pick 3 courses in it. Now most of the categories have between 5 and maybe 12 different courses you could choose from. Okay, so one criteria is that we have a couple carrots. It's just a little label on a course. I'll show you what I mean by a carrot in a second. But one of your courses of these 3 needs to be a carrot course. It's like we view it as like a center piece of the focus area. Otherwise, you can pick any other 2. Next, breadth area. So this is any course in mechanical engineering, 500 and above. Now, at 500 and above means it's a graduate class. And it's a course that it could be in the focus area, okay? It doesn't have to be, but it's a course which you can say, you can argue is it supports your focus area. It's useful for it. So supposing you were going into some sort of instrumentation, stuff, but you feel like, I need a course that helps me to design that stuff. Well, then you might that would be your breadth requirement. Okay, your added thing. It's not in focus area, but it's a useful thing for you to design instruments. Okay, so we'll get to that next. Now it gets very easy. Okay, this third one is 2 courses. Anything in mechanical engineering, 500 above, anything. Okay, so you're wide open. And you kind of want to be talking to your advisor, saying, you're looking at the catalog, what courses are coming up. And it's not, of course, hopefully don't just pick your easiest course. Pick the course that is going to be helpful for you in the future, so that when you go to get a job, you can say, I have this skill here. I've learned such and such. So things to talk with your advisor about. And the fourth one is even broader than that. Okay, it's any course in the graduate program, 500 above, not just mechanical. It could be, we have 3 departments. It could be also be in biomedical engineering, or it could be in ECE, which includes electrical engineering stuff, and computer science stuff. So it could be anything from all those. And it could be, I think it's a list on the next page of about 10 math courses we've approved, which are applied math stuff. So it's not like abstract math like topology or something like that. It's things like solving partial differential equations and stuff, things that are going to be extremely useful for engineering, or numerical analysis. Okay, and of course you probably have already guessed that most people for this number 4, almost everybody wants the math stuff. Okay, I'm joking. Okay, actually, one time some people felt that they had, because it was listed math, they thought they had to take a math. No, most people don't. But every now and then, I certainly have had advisees that want the extra math. And so we'll get to that in just a second. And the last one, you can take any course, graduate course in, say, physics or chemistry. And I think biology also, although I need to check that. But of the physical sciences is what I'm saying. Okay. Now, let's say if you're listening to me, you're a mechanical engineer. It's not all that easy to just jump into a graduate course, say in EE, because you may not, or programming, right? Maybe you don't have the full skills to take one of the, you might be able to take an undergrad, but that doesn't count here. So often a lot of people in the number 4 still take a mechanical, but they have the opportunity to do something quite broad. And then this last one, it's not an extra course. Okay, so if you count them, I got 3 plus 1, that's 4, another 2 is 6, another 2 is 8. Those are your 8 courses. This one here is just, it's one of those 8. You just got to make sure that one of those 8 satisfied what we call a practicum. It was introduced by the provost, I don't know, maybe 5 years ago. My recording right now, I don't know if I said it, is in February of 2021. Okay, and maybe 5 years ago, the provost said, across all colleges, departments, every master's program should have a practicum. And the definition of practicum is a little bit loose, but roughly it's this. It's a course which has a project in it, and the project accounts for roughly maybe a quarter of your grade. Okay, so we have a list of courses which we've approved, as practicums, and you just got to make sure that of your 8, one of them satisfies that. So we'll get to that in a second. All right, let's continue on this page here. So all this stuff pretty much describes what I was just saying. 3 courses out of your focus area, 1 course out of the breadth, 2 from mechanical engineering, anything 500 above, and 2 from either any engineering, including the other 2 departments, math, where the math is this list right here. Those are the ones that we've approved. If you find another math course, I might sign off on it. Okay, if I think it's you can petition things. Okay, not that petitions happen very often, but sometimes someone finds something that just, they, it's very important for they view their future career. But anyways, that's our nominal list. Okay, so so I do simulation of physical process. I teach a course in that. And so some of my advisees, I say, numerical analysis isn't a bad one, because you need to know the approximations that are going into writing a computer program. So I often say that, but there's probability, stochastic, which is time varying probability, um, just basic mathematical physics, you know, and then the practicum is one of these courses. So I didn't count them up, but it looks like 10 or 12 or something maybe. Um, I teach 4 graduate courses, and all of my 4 are a practicum. I believe in a project. Not everybody does, but I like it. So I usually give a midterm and a final, but I also give a project, and usually the project is kind of wide open that they can choose from. I find it a good growing experience for them, and I like interacting on it. Anyways, you can pick. We've got some good topics here. I think you'll agree. Um, Now let's go into focus areas. Okay, so we have 8 of them. Now let me just backtrack a little bit. So mechanical engineering, it's one of the oldest of all engineering um, schools that became a bachelor's and a master's and a PhD, going back to like 1800. And before that, I don't think they taught in colleges mechanical engineering. They taught other things. You know, colleges go back to time of Isaac Newton in 1600s and probably earlier. What did they teach? Well, they taught, obviously, that if it was Isaac Newton, they taught physics, some of the natural sciences they called it, but also literature, um, art. Okay, but engineering perhaps not. Okay, and what changed it was the steam engine. So we had the Industrial Revolution that took place around 1800, and people realized that they needed to train people in order to be able to make this amazing piece of equipment that was going to that did transform a lot of the world. Not just for so we have steamboats, we had steam trains that were super powerful. 1865, the train that went across the U.S. Transcontinental Railroad were steam engines. Things for digging, things for plowing, things for lifting, building. Okay, but we don't teach that anymore. We teach the thermodynamics associated with the steam engine, so the steam engine was the theory of heat. That was a big part, the Carnot cycle. Maybe you've heard of that sort of thing. Okay, how much, if I put some fuel into something, how much work, what's the maximum work I can get out of it? I don't want it to all go away as heat, you know. So it was kind of a heady thing, this study of heat. But in addition, it was also the study of like materials, making gears, making pulleys, making levers, and making them all come together. So you have like a chamber for the steam. All right, so all that became engineering. We don't teach it anymore, just the thermal part. The same thing is true in electrical engineering. So I believe electrical engineering schools began after mechanical. So I think we're older than that. I think it began around 1860 with the likes of Edison and Tesla and Alexander Graham Bell. Suddenly the world changed, and they needed people to really school them on how do you make all this stuff. But all that stuff I sort of mentioned, motors and generators, we don't teach that anymore either. Not really. We teach things about semiconductors and chips and light going through fiber optics, stuff like that. I think I've looked through the catalog and I don't see anything on how to make an electric motor. So these focus areas, okay, they are what has evolved from the beginnings of mechanical engineering. And they're the more relevant things. Mechanical engineering is considered, of all the engineering, to be pretty foundational. It's pretty tied to physics. You know, of course, it has applications and stuff, which makes it interesting in both ways. All right, so anyways, we've settled on 8 focus areas. So solid mechanics, okay? Now, 1, 2, 3, 4, 5, 6, 7 courses you could pick from. You could pick 3 out of 7. One of them has to be one of the carrot ones. So we consider the theory of elasticity to be super important in solid mechanics as to how, well, this whole thing could revolve around vibrations, for example. That's an important course, 515. You get jobs on both experimentally and theoretically knowing how vibrations enter into machinery and stuff. So 1 year, I don't teach that at the moment. Greg McDaniels is the professor. Greg McDaniels is the one who usually teaches it. Well, 1 year, I had 3 LEAP students I knew pretty well, and I brought them to Tektronix, which is outside of Boston here, and they needed people. They were doing studies on hard drives. They were making testing of hard drives. They run the hard drives for 24/7 for 2 weeks or something, and study all the vibrations and weed out the good and the bad before they sold them. All 3 of the graduate students got a job there, and they were very pleased with it. It's kind of a heady subject. Or here's another example of it. We are now getting to the era where we make lots of sensors. Okay, now that's sort of a MEMS area. This, if you see my wand cursor waving over here, I'll get to that. But little tiny things that can be like accelerometers. When you put the brakes on the car, it's a little chip that detects the deacceleration, and it tells it makes the seat belts turn on or the airbag go. So every car pretty much has an accelerometer, and your phones have about 11, as of right now, about 11 different sensors and actuators within them. Anyways, if you took one of these little devices and stuck it onto machinery, it's possible, there's patents on this sort of stuff, that it'll tell the health of that piece of machinery. It'll tell it maybe in 1 year of running, making parts and stuff, this thing is something's going wrong with it. And these accelerometers are picking it up. And so this theory of vibrations combined with being able to measure that stuff, that's pretty cool. And if it knows that you need to replace some ball bearings or something like that, or anyways, this is solid mechanics, kind of a foundational focus area. Next, biomechanics and biomaterials. We have a department of biomedical engineering, right? So the difference is a bit more that we're studying the properties of biomaterials. So like bones, ligaments, arteries, things like that. Like I heard a lecture maybe 2 or 3 years ago that to this date, we don't really know how tendons, when they've been injured, heal. They don't have blood supply. And this lady was giving a lecture here, and she said that she'd examined the healing of it using a scanning electron microscope. I think she said atomic force microscope. And it was a really neat study. And so here's another example. Your bones, I love saying this one. Your bones are a weak piezoelectric material. A piezoelectric material is something that there's like 60 different crystals that do this. If you squeeze them, they make a voltage and a current for a moment, the currents for a moment. So the old records, vinyl records, there's a needle that pumps along, so it's going up and down. Well, as it goes up and down, it makes a pressure in the needle, and that makes a current. That's a piezoelectric thing. And that's amplified, and that's what makes the sound. Edison's first records did not have that. He didn't have piezoelectric. I don't think he knew about it. The person that discovered it, the 2 people that discovered it, were the Curie brothers. One of them eventually married Madame Curie. It was 1880. discovered, yeah, 1880. Anyways, your bone is weak piezoelectric. So when you stand, you induce a voltage and a slight current for a moment in your each bone that's getting the stress. And it turns out that bone cells reproduce better under that environment. So walking, doing exercise and stuff is good for your bones because it stimulates that piezoelectric aspect and it stimulates the growth of the bone. And as you get older, it's not happening so much. People maybe have arthritis or other reasons they can't walk. And that's part of the reason why many elderly people have, their bones aren't so great. So anyways, that focus area, people study that. I think you can see there's jobs with that. And they don't just study it, they try to say, okay, if that's the problem, then what can we do about it? Okay. Acoustics. So we have some pretty good acoustic engineers here and professors. And, you know, at first blush, you might think that acoustics is, you know, an earbud or something, right? Okay. And it is that. I mean, that's been changing a lot. We have the wireless ones now. The integrity of these things is really good. The Apple ones that hang like this, the second version really keeps exterior sound out beautifully. And yet if someone speaks to you, it detects that still. It doesn't wipe out all sound. So that's a lot of acoustic engineering. Other forms would be, you could be analyzing a new auditorium, you know, that maybe shows are going to be taking place so that everyone in the audience gets a, you know, can hear it well. Another aspect of it, which I like to repeat, Professor Paul Barboni did something which I thought was very clever. So, you know what ultrasound is? It make, you know, so you look for in a baby in a woman's womb, for example, or you might be probing for a tumor. Okay, so they usually hold a wand, move it around your stomach or wherever it is you're supposed to be. So it's making pulses in the fluid, and those waves go in and reflect back out and you detect them. So now you can see a tumor with it. Okay, see the baby. Well, he realized that that the way the waves are reflected back off of it are different for a tumor or a benign tumor than a cancerous tumor because they have different elastic properties. And he knew this. I don't know how he knew it, but he knew it. Okay. So he put that into his detection system and his analysis system. So with his system, you can not only just look for a tumor, but he'll be able to tell you whether it's cancerous or not without cutting you open. So that's pretty cool. That's acoustics. Acoustics with, you know, a knowledge of elastic properties. Other sort of acoustic things would be sonar, okay, underwater stuff. And then, of course, just like with music and things like that, which is super important as well. This area here, thermofluid science and energy, I tell my advisees that if they're interested in green energy, you know, so, you know, there's so many things. So there's the solar cells, solar panels and stuff, right? There's wind turbines. There's geothermal means of getting energy from the ground. And these are all coming on board. Batteries. Batteries is a big thing. I mean, we have a professor here who's done a great deal of work on batteries. Emily Ryan, Professor Emily Ryan. And she's told me that within 5 years or something, the batteries, you know, lithium ion is what everyone uses, it's going to be like 10 times better than that once they figure out some of the bugs with it. And so that's all very important. So green energy, now look at some of these things here. It's not, some of it gets pretty deep, like statistical mechanics. I recommend everyone take it. It's a really good, it's very important material. Did you know that statistical mechanics derives thermodynamics? Yeah, and I don't know why, I think that's wonderful. All right, materials. I would say materials is a pretty foundational thing. it can be used in so many different areas. If you're improving on materials, it might go into something as simple as the bumper of a car, like throwing in carbon nanotubes into steel and getting stronger bumpers. That's pretty simple. How about bicycles? We all know that the materials there have changed a lot, not just in the frame, but also in how the gears and the chain and stuff like that have become stronger and lighter, and so they can, do a lot better. But then there's a lot of sophisticated. So one of our professors, Professor Basu, he and his a PhD student came up with a means of coating turbine blades. So think of the jets that fly overhead. Okay, and they have essentially turbines inside them, and they're spinning. So according with the theory of running these things, the efficiency of these turbines is roughly proportional to the temperature you can run it at. So if you can jack the temperature up, say by 25%, you'll have 25% more efficiency. Now, when you look at jets going overhead, you see all the exhaust. And it's not all exhaust, it's also hot gas, hot air. But let's face it, there's a lot of, airlines, I understand, spend about 35% of their dollars on fuel. 35%, something like that. Okay. So he and his doctoral student came up with a way of coating these things that would enable the temperature to go, I think he said 25% higher. And he had to analyze, they had to analyze what makes it still stick to the metal underneath it, what makes sure that there's no cracks that form, there's no faults that occur, on and on. They did all this analysis, and they got patents on it. Okay, so pretty important. MEMS and nano. Okay, so this is more my area. I teach a course. It's listed here, 579. Oh, it's got a caret. Good. Nano microelectronic device technology. So it's on chips. It's it's a very in terms of foundations for how much money is made in a year, it's huge because every computer has chips in it, especially the microprocessor, which is the most expensive one. They sell for $700 for a new microprocessor, and you got all the memory and things like that. So this area has been going on since 1980s, okay, something like that, early 1980s, the semiconductor part of it. It's probably the biggest money maker of all the stuff listed. But MEMS is very interesting. MEMS is it's bigger stuff. So if nanotechnology, where a transistor, a little device, is of the order of nanometers, usually MEMS devices are of the order of microns. So quite a bit bigger, like 1,000 times bigger. And MEMS stands for micro electrical mechanical systems. So instead of just running current like chips do, okay, they also have a mechanical component to it. Like they could be a little tiny pump. It could go in your artery and it help the heart or something. Or I believe this is considered MEMS. You know how they can put a small laser up through your artery to a place where there's plaque, like maybe near your heart. And you turn it on and it blasts, it vaporizes the plaque. It vaporizes it. It's a hard thing. This was quite something. They had to make sure that it didn't punch a hole in the artery, right? And they have to use a special wavelength, and they have to know a bunch of things about the material of the artery versus the plaque, blah, blah, blah. Okay, so that's an example of a MEMS device. Now, I said that our phones typically have like 11 of these things now. They've been increasing. So I'm saying this in 2021, maybe another year, there's gonna be more. But you know how your phone, a smartphone can tell how far you walked. It can tell your heart rate, It can tell how far you biked. I mean, some of it's done by GPS, but some of it's done by acceleration up and down, like climbing stairs. Okay, that's done with the accelerometer. And then also when you do this, you might be talking to someone and you go like this, it turns off. You know, the screen goes black. It's sensing your presence of your face. So those are all MEMS. And I would say that in terms of money, you know, the business end of it, MEMS is still pretty small compared to nano, the chips, I mean, but it's rising and it's exciting. It's people are just coming up with great uses of it. Okay, next one is dynamic systems and controls. Probably the biggest thing that people think of here is robotics. Okay, so that would go into manufacturing. It could be going into exploring, right? Either down deep in the ocean, on Mars, the Earth, the moon. Could be helping out disaster areas, right? Fires and things like that. We have as of a year ago, we now have a course on medical robotics, where the aim is to get to the point where the robot is doing the surgery, and it could be the doctor isn't even there. Sheila Russo is one of the folks, one of the professors. I think we have 3 professors that do a lot in this area. Okay. The other thing I should mention is controls. So it's where you're doing an operation and you put a sensor in there, so it gives information back to what's going in the process. And so it's a feedback. And there's a fair bit of math in that, or can be, depending on how it's used. For example, in my area of semiconductors, I might have a layer of silicon, and above it, I might have a layer of SiO2, which, by the way, is glass, the rust of silicon. Okay. And I might want to be etching a hole, making a little hole. When I etch it, I want it to stop on I want to say stop on a dime. I want it to stop on an atom. So it doesn't go any deeper into the silicon. So they have these sensors that as you're etching down, as soon as the silicon is being thrown out, it senses it and it stops the etching. So that's what I mean by feedback. Another example would be is you're landing a rocket on, let's say, the moon or something else. It's picking up, it has sensors, it's picking up cues from the ground below. And maybe you've got 4 rockets that are blasting, trying to keep the rock, you know, this thing all flat. And those, if I have 4 little rockets, and they all have to be going on and off just in the right way so that it lands flat. Okay, so that'd be feedback. Systems engineering is a study of looking at things in a very broad view, that many problems are solved in similar manners in a very systematic way. And these folks try to apply it to many different situations, the study of systems. And the last is manufacturing. Now, we might be changing this title somewhat, okay? I haven't, it may involve manufacturing something with design. It does have some design things already in it. So manufacturing, you know, probably the biggest thing about manufacturing is making sure that when you make something, that the parts or whatever it is, cars you make, the planes you make, the widgets you make, that the yield is high, meaning the percentage of good stuff is great. Now, my area of nanotechnology, chips, when they first start making chips, and any new generation stinks. The yield is horrible. It's like, it could be like 20% are good and 80% are bad. And there's reasons for it that I go over in one of my courses. But most manufacturing things are not like that. You know, most things you're talking about yields of 90% or something like that. So some of these courses also go into some more design type stuff. And people talk about designing for manufacturability. Like when you design something, you don't just want to make a cute thing that works. You want to make it such that when you reproduce it over and over again, that the yield is going to be really high. All right, so those are the focus areas. You should talk with your, I try to give examples. They all have job areas. I think you could sort of relate to what I'm saying. You could picture it. You should talk with your advisor about that. So I'm actually the main LEAP advisor in the ME. So I admit people, and then we sort out we have like 5 advisors, okay, and we figure out who should be taking this particular person, trying to match them up with those skills. But most LEAP students don't really have a good idea of these 8 things. So that's part of what I wanted to create this video for, and hopefully it's helpful. All right, so now let's go back to this. So this is without a thesis. Now most master students don't do a thesis. So supposing 35 graduate in a year from mechanical engineering and get a master's. Typically our numbers are like 2 or 3 do a master's. Do a thesis, okay? And I'll tell you, I'll give my recommendation. Maybe your advisor will say it a little bit differently, but I'll give you mine in just a moment. But in terms of how it fits into this thing, it's only this category that changes, that bottom one where my cursor's going, number 4. So let's go to that one. Oops. Sorry, my Zoom menu just popped out. There we go. Okay. So there it is. And so number 4 is what changed. Remember the number 4 was any course in any engineering thing plus those math ones, which we definitely want, and physics and chemistry. Okay, so instead you're going to do 2 semesters of a 4-credit, sort of like an independent thing, but it's called MS Thesis Research. And that's what you replace it with. Now, a lot of people need more time than this. They don't get it done. It's more work, and which is probably why we only have 2 or 3 out of 35 in a year that typically do this. But yes, this is what you do, okay? And it would be, you want to find someone, a professor, who is going to supervise it, who's going to work with you. Usually you meet with them, say once a week or something like that, and figure out what else you need to do, how's it coming along, that sort of thing, okay? And the advisor gives a recommendation for next steps. It can be great, I mean, research can be a lot of fun. It can be very exciting. So here's my view on it. First, you shouldn't feel pressured to do a thesis. Most masters in any, whether it's engineering or whether it's physics or chemistry, most masters don't do a thesis, okay? But some do, obviously. For your doctorate, of course, you have to do a thesis, right? That's required. I would suggest this. If there's something that you find in, say, in the first semester, that you just like, I love this topic, I just got to do it. And you find a professor who is willing to work with you on it. And you would do it even if no one was paying you to do it or something like that. Then do it. It's a great experience. Go for it. In addition, please, when you go for your interview in your job, make sure you mention it. I've had students who do a thesis, they go on the interview, don't say a word about it. Now, that's silly. You want to highlight it because you've done something special. Okay, so bring it out somehow. So that's my recommendation. Now let me point out another thing. The focus area, that is not seen on your transcript. I mean, it is on your transcript, it's the listing of courses, but on your diploma, it's not said. Okay, so supposing you took a focus area in robotics, okay, it's not listed. So when you do your resume, usually in the resume, they say, what are your, you would write down your key skills, key knowledge area. You would say, I'm expert in robotics, I've taken medical robotics, or I've done other things, So you want to make sure you highlight it, because otherwise You have mechanical engineering masters, which is great, but you haven't shown, you haven't told as much as you could. All right, last one, PDM. So product design and manufacture. Now we've had this program a few years now. Okay, most schools don't have this master's program. Now, almost any engineering school has mechanical, almost every single one. Some universities have things we don't have. We don't have a chemical engineering one, for example. We don't have a civil engineering one. We've concentrated on these three: electrical, mechanical, and biomedical. So we now have a master's in product design and manufacture, thinking that it's a good compatibility. You design things, but you also know how to make a lot of them and make them, well, but cheaply and fast. That sort of thing. So the designers of this program, I was on the committee, by the way, although most of my suggestions were overruled at the time. But they put together, they felt that if you're going to call yourself a product design person in manufacture, you darn well better have certain courses. So there's 5 courses you have to take. I remember the other one we had, you had 8 possibilities, and every single thing, whether it's a focus area, you pick 3 out of maybe 10, right? The next, you had a lot of flexibility. This one you have much less. You have to take 5. And it could be you really like these 5. Like there's 2 courses in advanced product design. Okay, that's 691 and 692. There's another one, product realization, which is, I understand it, is we use rapid prototyping but make a lot of the things and see how the consistency is going from one of them to the other, and then analyze it in gory detail so you really get a feel for why the variations they always vary. There's always some variation, and pick a car, make another car, they're not exactly the same. Why? All right, so you got to take those 5. Then you can pick 2 courses in design and manufacturing. These are 500 and above, and there's a list that you can pick from. Let's see if I can get to that. Right here, this is your list. And they're listed for, these are the ones in the fall, these are the ones in the spring. So you can pick 2 from all that stuff. Okay. And then you then have one open one, which is engineering in general or physical science, just like in the other one. So this one's the most flexible category right there. In the practicum, you don't have a choice of 8 or 10 or whatever it was. You have to take that one right there, product realization. That's your practicum. Okay. So pros and cons on this. And you should talk with your advisors about this. And I'm going to try not to sway one way or the other. If you are going to go get a job in product design, which is not easy. Okay, a lot of people love this thing. They want it. It's an exciting thing to make new products that might go in the home or the automobile or the garage or sporting goods or whatever. It's exciting. It really is. Very creative. You may change. Those earbuds we're talking about. That's product design. It's product design plus acoustics, I guess, right? So that's good. So if you're going for a job in product design, I believe that they would be very, very impressed that you have a master's in it. Okay, so that's good. That's a real plus. And I think the same thing true with a manufacturing job. They'd be very impressed with that. And there are a lot of jobs like that. We had 2 students who worked in Fraunhofer here. I'm not going to go into what that is, but it's behind the glass wall that is in 15 St. Mary's. And these 2 guys worked there for about, I think, 3 or 4 years. And then they applied to Tesla. And they both got a job there within 2 months of each other. and it was in the manufacturing sector of Tesla, which is pretty cool. Yeah. Now, the other qualification, sorry, I like this joke. Each of their first name was Ian. So you probably should change your name to Ian if you really want to. Obviously, it's a bad joke. All right, let's keep going here. So a con, supposing you go through all this, okay, and you get your master's in it. I think if you went to other places like GE or Raytheon or something like that, they might say, I've never heard of a master's in PD now. Now they have manufacturing areas there too. They might like it, but mechanical is definitely more recognized. It's been around since 1800. Okay, everyone's heard of it. So you would need to wrestle with that. Make sure, put your best foot forward and explain it and so on. It's nothing to feel embarrassed about. I don't mean that. It's just that the hiring person may not be fully aware of what it is. Okay. Again, if you're applying to a product design place, I think they'd be overjoyed. Also, though, if you go to a product design place, make sure you get a portfolio. You're not going to get a job without a portfolio, which describes projects you've done. And we have some videos and things like that on it. I've made a video on it at one time. I think I pretty much finished what I wanted to do. So you are welcome to shoot me an email and ask me questions if this brings up some questions in your mind. Anna Maslin also knows a great deal about the mechanics of all this. I'm the one that, at the moment, I'm the one that signs off on it at the end. With your advisor first signs on it that you filled out this, you made the right selections of courses and stuff, and I sign off on it, and then you get your diploma. So feel free to ask me questions or your advisor, but hopefully this has been helpful. Thanks for listening, and hope to see you around. Thanks. Bye-bye.